Okay, thanks, Charlie. I've been coming to these meetings for, I think, on the order of 12 years now. And our conversations used to start out with, is there a need for forecasting? Boy, we've gotten beyond that. You know, not only is there a need for forecasting, but there's been a lot of effort on reducing the error in terms of both wind power forecasting, solar power forecasting, et cetera. We're providing probabilistic information. We're trying to understand how the markets and the utilities might be able to use that probabilistic information. We've had conversations about impact of climate. We've gone a lot of directions, and forecasting has continually improved as we've had these conversations and understand what the needs are. So when I'm asking you what the needs are, it's because we want to be able to respond and be helpful. So today we're going to talk about some of the advances that are happening in forecasting, how we're responding to some of these things. We'll be starting out with Dev Millstein of Lawrence Berkeley National Lab, talking about a comparison between various models and what might work best in terms of using base models. Then we'll have Craig Collier talk about a particular extreme event and the problems it made on a particular system. And again, how can we improve forecasting to deal with these things? Then Daniel Palmer of Upstream Tech is going to tell us about how they're forecasting for the forgotten renewable, hydro. Okay, usually we've been thinking about hydro as a constant, but Daniel will tell us that's no longer true. We can use hydro in balancing. And then Dave Turner from NOAA will come back and tell us about the latest advances in probably the most useful base model in the US, the high resolution rapid refresh that is turning into the Rufus in the near future. And he'll tell us what that means. So Deb, you have the floor, and we're looking forward to hearing about evaluating the ability of MET models to characterize daily cycles in wind generation.
All right, thank you, Sue. Let's see. Oh, okay. All right, thanks for having me, everyone. It's really great to be here. I'm learning so much being here. I really appreciate it. I'm Dev Millstein from Lawrence Berkeley Labs. So we all know how important it is to understand temporal profiles of wind power. I'm going to be focused on wind generation and meteorology for wind generation assessment in this talk. But I just want to mention I'm looking at a different angle than just forecasts here, because both forecasts of wind profiles, so what's going to happen tomorrow or in the next hour, but also understanding long-term retrospective profiles of wind. Both of those are very important for integrating wind into the system. I'm going to be looking at the more sort of retrospective, real-time meteorological data products. So looking at two reanalysis models, ERA5 and MERA2, and also the HRRR model over the past few years, and how those models represent wind resources for wind generation. So the biases and errors here that I identify should really provide important context for understanding and improving forecasts as well. But this will be a retrospective focus, not of real-time wind speeds, not of forecasts. Okay, so the main challenge here is that it's really hard to evaluate meteorological models unless you have private data. Publicly, there's only a handful of tall tower measurement sites that provide wind speeds at hub height or higher. Surface wind speeds at 10 meters just provide very limited information into the patterns you see potentially above the boundary layer at 100 or 150 meters at the top of the tip height. So the main thing I'm going to be showing today is using generation records to help evaluate the meteorological models. So we see here we have tall towers are in the order of 10, which is that top figure, one example of a repository of tall tower data. And the bottom is a figure of all the wind plants in the US. And we can see that there's, order 1,000 of those, and they're spread out all over the place. And the tall tower locations are just not sufficient to really get an assessment of the models over all the different wind plant locations. So what I'm going to do today, I'm going to take meteorological model wind speeds at hub height and use a very simple generation approximation using a power curve appropriate for each plant and get an hourly generation estimate out of that. And I'm going to compare that to the recorded hourly generation, but after we've adjusted those records for curtailment, because obviously the meteorological models do not account for curtailment. So we want to compare apples to apples. So we remove that curtailment. I'll start with looking just in ERCOT because ERCOT provides plant level hourly records of generation and curtailment, which is very useful. Thank you, ERCOT, for doing that. One detail about the method here, I want to just talk about the transformation of wind speed to generation. We use a very simple power curve that's varied by the specific power of each plant. So that's the rotor size relative to the capacity of the turbine. The reduction of specific power over time, or the movement to relatively larger rotors, is sort of one of the largest trends we've seen in wind power deployment or plant design over the past decade and a half or so. And so that is something we do capture with this, but we do not capture a lot of other sort of detailed aspects of generation modeling like wake losses or turbulence, wind shear, et cetera. Okay, so in ERCOT, this map here shows about 100 plants, slightly more than 100 plants that we looked at. This is all this research for this ERCOT portion is published in Wind Energy. It's publicly available. The first thing I want to talk about is just general error, model error here. And we calculate this as the capacity factor of the model minus the capacity factor of the actual recorded generation at each of those plants I showed for each hour. And this figure covers 3 years here. The sort of blurry gray area are individual lines for each individual plant, and the dark black line there you can see is the average across all the plants in ERCOT. And the main takeaway here I want to talk about is the difference between hourly and daily air for these models. And we're looking only at 2 of the models right now, MERA2 and ERA5. And the main, and if we overlay them, we can see that the hourly air is much wider than the daily air, which is that sort of light blue line underneath the hourly air. And specifically, that means that the probability of getting a capacity factor within plus or minus 20 capacity factor percentage points of actual for daily is 99% for ERA5 and close to that for MERA2, but for hourly it drops significantly down to 78 and 70 for ERA5 and MERA2, which means on an hourly basis, you are quite often, even without any forecasting, this is just retrospective analysis, getting capacity factors, errors of 20 percentage points, which is pretty large. Now, how does this evolve during the day? What are the diurnal effects or trends here? And for this, we did a new sort of time marcation here where 0 hour is sunrise. So that line in the middle of each plot is sunrise. And then to the left is nighttime and to the right is daytime. And so first, let's look at the root mean squared error here. The modeled root mean squared error is much lower during the daytime. It drops significantly after sunrise compared to the nighttime. Similarly, for the correlation is much improved during the daytime. And we see that a big swing and particularly connected to sunrise as well. The mean error, So the mean error here, this is not adjusted for losses, so I don't think it's important to look at the absolute values. We'd actually expect both these curves to shift down closer to 0. But what is important with the mean error is that it has a really strong diurnal cycle, especially for the Mera product here, which is really associated with sunrise. There's a big inflection point right at sunrise. Now, if we bring in the HRRR model, HRRR model, and compare the three, just looking at correlation in this case, and also with this soul time metric, we can see that all three models have this strong association with sunrise, that all three models have much better performance in terms of correlation, at least during the daytime versus nighttime. And we also see a seasonal component where summer nighttime has the lowest correlation across all three models. We also see that the HRRR model has much higher correlation than MERA2, and ERA5 is in between, and that also matches the resolution of the model. So as you go left to right here, you get to more finely resolved meteorological models. But the high resolution of the HRRR model does not solve the summertime, nighttime correlation decline. So just to sum up a couple aspects of the ERCOT plant level comparisons, we see hourly correlation and root mean squared error worse during nighttime than daytime. Correlation improves with model resolution, and the daily errors were much smaller than the hourly errors. There's a lot of future interesting questions here, which I won't have time to get to. All right, I want to move on to discuss other regions. This map, all the little dots there just show all the wind plants that we looked at. We use a slightly different approach for looking at other regions. And the reason we use a different approach here is because we don't have plant level hourly generation. So we have to compare to regional generation records. And those are for each hour. In order to make that comparison, we model each of those wind plants in the same way we did before, except in this case, we did this a little more recently. So we added a little loss adjustment just to make the biases closer to reality. And then we sum across all the plants in the region and compare the region-wide hourly generation to the reported region-wide hourly generation after adjusting for curtailment again. I'll just skip that detail for now. So across the center of the country, this is ERCOT, SPP, and MISO, and PJM, which stretches to the Atlantic coast as well. We see that the models do a pretty decent job overall of reflecting the diurnal cycles in wind generation. These are no longer based on that sunrise time, but just local hourly time. I just want to zoom in on one. This is from MISO for Q3. And you can see that ERA5 and MERA2, ERA5 and HRRR both match the shape pretty well of the reported generation. They're just shifted a little, and that shift could possibly be because we have a slightly different set of wind plants than were reported on. So the main thing I'm looking for here is that the shape is similar. But we see that the MERA2 model really, even in MISO, does not represent the diurnal profile very well. And we look back across the other ISOs and we see the same thing where sort of MERA2 here, the yellow line, is bouncing around from the bottom to the top of the range between the models and the reported value, which means it's not doing such a good job of representing the diurnal cycle. Okay, now we can look to more challenging areas to model, and they're challenging, I think, primarily because the topography is more complicated. Here we see the reported and the three models as well. And what we can see here is that the HRRR model is doing a pretty decent job of resolving the diurnal cycle in these regions. There's biases, of course, but there's sort of extreme biases from ERA5 and MERA2. This likely has to do with model resolution, but it's not just biases that we're worried about here. We also see that this pointer is hard to move, but we can see the shape doesn't really match the diurnal shape that's in CAISO, for example, it's peaking during the middle of the day instead of at night. That's not good. And we see similar problems in other regions as well. So in this situation, the HRRR model is really differentiated, more differentiated from what we saw in the early analysis with ERCOT, in that the HRRR model is at least more or less representing the diurnal shape of the wind generation in the region. So just a quick note, if you want the data that we use to do these comparisons, it's publicly available at this data repository. It's part of the Department of Energy's Wind Data Hub. So feel free to go to this website and download it. This will be just the hourly modeled wind speeds at all the plants shown in that map, and also the estimated generation given our choice of power curve and the simple loss function and adjustment for the air density. Yeah, feel free to email me if you have questions about this as well. Okay, so just to conclude here, in the plant level comparisons in ERCOT, we saw that models performed worse during nighttime, especially summer nighttime. We saw the more finely resolved models performed better overall, but that the higher resolution did not solve the summer nighttime issues. The daily errors, though, were much smaller than hourly errors. So depending on what time frame you're interested in, that can be an advantage there. The regional diurnal cycles, looking outside of ERCOT, we looked at region-wide diurnal profiles of wind generation. HRRR performed the best in all cases, but it was most differentiated in the more challenging regions like California and the Northeast, where MERA 2 and ERA 5 really did not perform very well. They did not represent the diurnal cycles. And if you'd like to use that data, it's publicly available, very simple to use as CSV files. So thank you to my co-authors at both UCSD and also LBNL, and feel free to reach out to me with questions.
Perfect timing. Really appreciate that. And that's going to form a basis for some of the rest of the conversation. Okay, next up is Craig Collier, who is Chief Meteorologist and Head of Operations at Energy Forecasting Solutions. He's going to talk about a particular extreme event, Winter Storm Elliot.
Thanks, Sue, for that introduction. Yes, I'm going to talk today a little bit about Winter Storm Elliot, some of the details around its origin, how the storm came to be, a little bit about some of the difficulties and the challenges of forecasting the associated hazards to wind energy, and then additionally, I'll speak a little bit about the uniqueness of the storm historically. So let's see here. Yes. Yeah, so Winter Storm Elliot was the product of the clash of two air masses, or what we call differential thermal advection. Put simply, we had very cold air descending from the Arctic to the south, and it butted up against very warm and moist air coming up from the south to the north. And in these contour maps of sea level pressure anomaly, you can see that over the course of about 6 days, high pressure over northern Canada is sort of stationary there for the first 3 days, starts to move a little bit to the south on the 21st and 22nd, and really sort of approaches an area of low pressure that develops in the southern United States and moves up towards the Great Lakes on the 22nd, 23rd, and on the 24th. The difference between the pressure anomalies, or ultimately the difference between the pressure between the high pressure center and the low pressure center accounts for a very large pressure gradient, and it's sort of maximized on the 23rd, which gives rise to very strong pressure gradient winds. But in addition, this particular air mass that came from subarctic region was quite cold, and the planetary wave pattern at the time sort of allowed it to remain fixed in place for about 2 to 3 days over northern Canada. And there was, of course, a lot of snow cover on the ground over that region during that time, and a positive feedback sort of developed in which the snow cover helped to continuously cool the air mass and dry it out. And so the result was, after about 3 days, we had a very cold and dry and ultimately very dense air mass that once it was allowed to move thanks to a buckling in the planetary wave pattern, it had significant sort of forward momentum that sort of added to the overall pressure gradient force related winds that were observed at the surface once that high sort of came and approached that area of low pressure. So the result was a storm system in which we had the bulk of the strongest winds in the coldest air. And so that was a little bit unique relative to, say, Winter Storm Uri, which we've talked about 20 months prior in February 2021, wherein for that storm, a lot of the wind was out ahead of the cold front. So out ahead of the sort of in the warm sector of the storm, along the cold front and a little bit behind it in the cold air. For Elliot, it was very different. A lot of the wind was associated with the cold air mass, and so well behind the front, and it persisted over areas in sort of the cold sector of the storm for quite some time, for about a couple of days. During the peak of the event, we measured the pressure gradient across Iowa, about 500 kilometers west to east, to be on the order of around 20 millibars. That's very high. That's sort of something you might see in sort of a budding Cat 3 hurricane. So very significant winds associated with the system just due to the pressure gradient force alone. So there were 3 primary hazards associated with this storm that were distributed geographically across major sort of power systems in the US. The first of which I would say is sort of a tertiary effect was freezing rain and icing. And that affected primarily portions along the southern edge of the coldest air mass. And that's indicated by sort of the green dots in these maps here that are a little bit difficult to make out. But those sort of green dotted locations indicate areas where there was icing or freezing rain observed. So some wind plants did succumb to that, but it was really more of a tertiary effect. The secondary effect was the cold air itself. So it was a very cold air mass that, again, affected some of these wind generating regions in the northern US. Temperatures in the coldest of the air mass, sort of in the very northern parts of the region affected, parts of eastern Montana, the western Dakotas, as well as even into Minnesota, did experience temperatures down between -20 to -30 degrees C. So sort of approaching low temperature shutdown conditions for even winterized projects. Further east, where the air was a little bit warmer and we didn't have as much exposure to the coldest air associated with this air mass, temperatures were still in the -10 to -20 degrees C range, which was sort of approaching the low temperature cutout conditions for non-winterized projects that we found more commonly sort of in northern Appalachia, the Alleghenies of western Pennsylvania. So those projects, even some of those shut down due to low temperature thresholds being met. But even once the air mass sort of modified and some of the coldest air receded to the north, we still had persistent wind, very high wind over a very large region of the northern United States. And as indicated by these red dots in these sequential contour maps, there were locations here where sustained wind was in excess of 21 to 26 meters per second. So higher than sort of the high wind cutout thresholds for most wind projects in the region. If we consider just one wind project on the western edge of the domain affected by Elliot, this is a project that that was significantly affected mostly by high wind cutout. If you look at just the sort of turbine average wind at hub height from turbine anemometers for this particular project during this event, you can see in the top left, very significant increase in wind going into the day on the 23rd. That did exceed very briefly 21 meters per second of the sort of high wind cutout threshold for this project, indicating that if we were to just simply diagnose high wind cutout at this project using mean turbine anemometer wind speeds, we would definitely capture it. There would definitely be an indication for a high wind cutout. But if you look at the variance of wind across the project, which we try to account for in forecasting, you see that the range of wind speeds measured by all turbines of this project was quite high. And in fact, it was around 10 to 15 meters per second, just in the range across the project, which was significant. And at the peak of the event, there were a large number of projects that, a large number of generators that were offline, even though the average wind across the project wouldn't have indicated that we were at high wind cutout thresholds. So if you were to sort of take your average wind and sort of apply a power curve to it for this project, as shown in the lower left, our green curve indicates sort of what would happen if you were to just simply assume you had a perfect forecast for the average wind of the project. Yes, we would have captured the initial sort of high wind cutout for this project occurring early in the, midday on the 23rd, but later in the day on the 23rd and through the 24th, we would have, the forecast would have been off by about 100% just due to all the partial high wind cutout that occurred for the project, just simply due to either subsampling the wind at that project or using only the average. So the power forecast here was large, even if we had had a perfect meteorological forecast for the average wind of the project. To the east, another wind project that was affected by this storm. This was in Western Pennsylvania. Similar story here, except that the average wind at hub height never really exceeded the cutout for this project, which was at 26 meters per second. If you look to the top right at the overall range of a wind across the project is measured from all of the turbines, and this was a somewhat smaller project, the range was fairly significant, again in the order of about 10 to 15 meters per second. And there were certainly some turbines that were in which winds were exceeding the high wind cutout threshold. So this is a project in which if you would just use the sort of hub height average across all of your turbines, you would have missed the cutout event entirely. Now, this project was also affected pretty significantly by low temperature shutdown. It wasn't winterized. It did experience temperatures in the range of minus 20 degrees C. And so you had two sort of effects here contributing to a fairly large shutdown of this project and fairly large forecast error. Again, if you were just assuming a perfect wind speed forecast for hub height at this wind plant. So the area really affected by Elliot and sort of in that sort of high wind cutout, I would say risk zone, consisted of about 13 states from the Dakotas all the way to Pennsylvania. And so this is a region that is, in which there's about 45 gigawatts of wind installed, about half of which cuts out at 21 meters per second sustained wind, and the other half of which cuts out at about 25 to 26 meters per second, just based on the technology across this domain. If you were to look at this domain and average the wind assessed here, and this is using a product that Deb was just talking about in his discussion. This is from the HRRR, the initial condition from the HRRR model. You see that if you were just averaging across latitude over the domain affected by Elliot, you would have what's sort of a longitude time, a time series here. So looking to the early hours and days of the event, from say the 19th to the 21st, across longitude here, there's not a lot of wind. It's fairly calm, and there's in fact some areas that are probably not even experiencing wind at cut in. But once you get to the midday on the 21st, we start to see the wind really increase in the west, and then we start to see high winds really spread to the east. And it's given sort of by the diagonal nature of this warm contouring. By the 23rd, there's almost a stalling of the high wind or the maximal wind. And that's a bit unique in the sense that we've got maximum wind sort of being achieved from an area spanning the central Dakotas all the way to central Pennsylvania. And that, of course, sort of shrinks in size or coverage as we go into the day on the 24th. During this particular period, we've got a lot of simultaneous wind cutout. And if you were just, again, applying this HRRR initial condition wind speed to all of the technology, all the power, all the wind power in this particular domain, you would see that the risk for high wind cutout is very high. It's on the order of about 14 gigawatts. And that's even accounting for some of the intra-farm variations in wind speed. So there were predictability challenges just associated with getting the wind speed right. And so in addition to temperature, this is a day ahead forecast for the entire domain. This is 45 gigawatts we're forecasting here during Elliot. You can see prior to the passage of the cold front, we're getting in the day ahead forecast the variation of wind just about correctly and the ramp timed fairly well. But once the cold front passes, that ramp occurs and we start to get a lot of low temperature shutdown, particularly in the northern part of this domain. And so the forecast models were biased high with temperature. So we had to make some adjustments for that on this day, which helped our forecast to converge more closely to the actual generation occurring after accounting for a large amount of low temperature shutdown that wasn't seen in the forecast models. And then once those forecasts converged, we had a growing divergence of the forecast going into the day on the 23rd and on the 24th. And that was due to additional high wind cutout that persisted and again was under forecasted due to an under forecasting of the wind and thus an over forecasting of wind generation. So what model did well with this cutout event? So if we looked at, we consider we have sort of a conservative and an aggressive estimate of the wind generation cutout associated with Elliot as given by the blue and green time series here. These are sort of static, presented for 7, 5 to 3 day ahead and 1 day ahead forecasts. You can see that the GFS model here, this is actually not showing up on the slide and sort of the labeling, but this GFS model forecast shown in the top row indicates very little high wind cutout in its forecast, really only showing up at a minimal amount in the day, into sort of the 72-hour ahead forecast, and then again in the day ahead forecast. The GFS ensemble, which is just an ensemble of the GFS ensemble forecast model or ensemble forecast system, shows even less high wind cutout and only really showing a minimal amount in the day ahead forecast. Really only the European Center's high resolution deterministic model shows a significant amount of high wind cutout, and it's timed not particularly well in the 7 day ahead, the 5 day ahead timeframes, a little bit too early. Perhaps the model sort of was either forecasting the front to move through a little bit faster or located the wind primarily along or just in advance of the front instead of behind it. But in the 3 day ahead horizon, the model comes into fairly good agreement with what we estimate actually occurred relative to high wind cutout, with forecasts sort of falling in between our conservative and least conservative estimates of the cutout that occurred. And unfortunately, I don't have the day ahead for this particular model here. It's missing from my archive, but suffice to say, this model was relatively superior to sort of the medium range to long range NOAA models that we looked at. How common is this kind of event? So looking back over the past 4 years, there have been 4 events that put at least as much generating capacity simultaneously at risk for high wind cutout. There was one in February of 19, and 2 in 2021, and 1 about 8 months prior in the spring of 2022. But I would argue that those events are really they're significantly different from Elliot in the sense that while they may have put at least as much sort of generating capacity at risk due to high wind cutout, they didn't have the geographic footprint that Elliot had. So as I showed you earlier, there was a coverage from pretty much the Dakotas all the way into Pennsylvania for very high winds and high wind cutout risk that we just didn't see in the sort of more recent 3 events, one from the spring of 2022 and the 2 from 2021. Certainly very high winds, and particularly in the western part of the domain affected, but there was more of a movement, certainly from west to east of the high wind cutout risk, and not sort of the stationarity that we saw with the risk in Elliot, which I think caused major problems in terms of planning and certainly put stress on the flexibility of power systems. So that's all I have. Thank you.
Thanks, Craig. A huge impact from a single event. We need to be able to get those events better. Okay, next up is Daniel Palmer. He's business and development partnerships in Upstream Tech. He's going to be talking about forecasting for hydro in an increasingly climate-stressed environment.
All right, good morning, everyone. I recognize I am the odd duck here talking about hydro and water. So hopefully I think a lot of what I'm going to talk about is going to be probably things folks have heard before, but maybe from a slightly different perspective. I hope you'll all stick with me for the full talk, but if you don't, here's what I'm going to say in about 3 or 4 sentences. So we have historically relied a lot on hydro as a renewable and dispatchable resource. It plays a really important role, but water is becoming more volatile than ever. And the models that we've traditionally used to forecast water availability are not able to keep up with that change. The good news is that there are new methods out there that show a lot of promise, and that as we move to a grid that is more dominated by renewable resources, we can actually have hydro as a really strong part of that, and better forecasting can play a key role in that. Cool, so let's dig in a little bit more. All right, so setting the context. We are, as everyone knows, increasingly having more intermittent resources on the grid, which means that as we move to a fully renewable grid, any sort of firm or dispatchable carbon-free resources are going to be increasingly important. So that ranges from traditional things like hydro to other new forms of storage. We're seeing this happening already in real time. So I know there are folks from California here who experienced this, live in real life last summer. But during a heat wave last summer, there was a point where the state of California was texting folks, asking them to help shed load, and the grid was sort of really stretched to the end. During that period, hydro played a really key role. So this blue line at the top that you can see is Idaho Power's hydro resources, really helping carry the grid through one of these really stressful times. That's great, that's what we want, right? As we have more stresses on the grid, having resources like hydro that we can dispatch, help come to the rescue, everything's great. Obviously, not so fast. Overall, water is more volatile than it has historically been. Again, folks in the West, this is not news. You've all lived through 2017 floods, last few years, mega drought, this year, just crazy amounts of water. We're seeing more and more of these hydrologic events, storms, flooding, droughts, they're becoming ever more common. Beyond that, though, the models that we have to predict how water is going to behave are breaking down. So the future is getting wetter and drier, hotter and colder. Even the world's best weather models often disagree about what's going to happen over the coming hours and days. But even beyond that, the fundamental relationships between things like rain or snow in a watershed and how much water actually makes it down to the river or to the dam are breaking down. So in 2021, for instance, in the Colorado River Basin, we had about an average year of snowpack. We got about 80% of average. And so the model said, great, things are looking good. But what actually happened was we got less than 50% of the water that would have been expected for that. So you have these really high temperatures, you have dry soils, you have wind blowing dust onto the snow. And all that means that our traditional models saying, okay, we've stuck a stake in the ground and we have this much snow, so we should expect this much water, those aren't holding true anymore. And so we need to look to new methods to actually be able to understand what's going to happen both meteorologically, but also in that translation from water coming to the ground for how much of that is going to make it down to our hydropower resources and when. Good news is that there are new forecasting methods that are showing a lot of promise around being able to improve that translation. So again, folks in this room could probably teach me some of this, but sort of taking it all the way back to different methods of forecasting. The traditional way that you would forecast water availability is using a physical or a conceptual model that explicitly represents different things that we know are happening in the atmosphere and on the ground. and using those to calibrate models, typically for individual watersheds or basins, to say, okay, based on this expected precipitation and temperature and all these other variables, here is what we expect from a runoff or from a flow perspective. The challenge is that as conditions change, you both need to recalibrate those models, which can be very expensive, it can be very time consuming. And as we experience conditions that we haven't seen before, as those relationships break down, if your models aren't able to represent that, you're going to be in trouble. On the flip side are all the futurists saying, great, let's just, let's bring a lot of data in. Let's take a statistical approach. Let's see what has happened historically. Bring a lot of data, machine learning, AI, all the buzzwords. And then those models on their own are going to be smart enough to tell us what's going to happen in the future. Unfortunately, that doesn't typically play out. There's a tendency for models like this to just learn, okay, what has happened in the basin before, match that pattern, and say this is what's going to happen again. And in a world that is changing and becoming more extreme, that actually doesn't always work. You also don't always know why the model is doing what it's doing. And so when you're making really important decisions like trying to prevent floods or dispatching resources during really important times, you want to be able to actually look into the model and make sure that what it's doing is reflective of what we know from a scientific perspective. The spoiler here that I'm here to say is you can actually get a lot from bringing the two of these together. And so we call this theory-guided machine learning. And the approach that my team uses is to have a statistically based model that allows you to bring in a lot of new data. So it allows you to say, okay, we know in this changing world, the more relevant information we can use across a broader training set, the better chance that we have of being able to pick up on these unique new patterns that are emerging in these extremes. But we don't just grab a bunch of data and dump it into a model and let it go do its thing. It's really important to have folks who actually know what they're doing, hydrologists and water resource engineers, be able to interrogate the model at each point and make sure that it's reflecting what we know about hydrologic science. And it's important to do this across a really broad set of basins. So your risk of pattern matching decreases when you have a much broader set of data because you're seeing more unusual circumstances. My team has moved this beyond just sort of theory. So we, a few years ago, published some papers around this as a concept, and we've spent the last few years actually putting it in practice. So moving that research to operations. Right now, our models are live on 5 continents. We haven't yet gotten South America, and forecasting in Antarctica is obviously its own unique case. But the good news is that by bringing these new perspectives into play, you're able to help, whether you're working in operations or in trading, you can see more confidently and further into the future what's going to be happening with your hydropower resources. It's one thing for, Sue Ellen said, I come from the business development world, so it'd be easy for me to sit up here and give you all the pitch about the things that we're doing. But this is obviously a really important field, and it's one where, the only way that you can build confidence in your work is to share your methods and to evaluate as rigorously as possible. So the Bureau of Reclamation a couple of years ago set up a competition where every day for a year at about 24 sites, different forecasters would submit their forecasts for the coming 10 days. And then a third party would evaluate, okay, how did everyone do? And so this theory-guided machine learning ended up actually performing really well across a wide variety of hydrologies. So areas that are mountainous with a lot of snow, areas in the southeast that get a lot of flashy rainstorms, up into the north and into the plains. And in 23 of 25 different categories was able to be the most accurate forecast. Digging in on what that looks like in a sort of specific example, I know a lot of folks here are from the West. So across the sites in the Western US, there was 4 different categories of model. First, you have sort of the standard statistical. This is the like newfangled AI can solve everything. Let's just hire a computer scientist who doesn't actually come from this world and, you know, put them to the task. And those were the least accurate models that we saw. So I'm here to say AI machine learning can be really powerful, but it's really important to know what you're doing with it. And it's important to have the domain knowledge when you do that. The National Water Model and NOAA's River Forecast Centers, two of the best models out there, did fairly well. The River Forecast Centers especially are really well tuned to the sites that they're working at and bring a lot of expertise to the system. This theory-guided machine learning model was able to bring even more skill. So if you look at the spring period when you have all the snow that is melting out, you know, big gushes of water coming down into reservoirs, our hydro forecast approach was able to reduce error by 41% compared to river forecast centers. It's one thing to look at the coming days ahead, but as you're trying to plan for what a grid looks like over the coming months, looking seasonally is really important as well. So, you know, if you're in the water forecasting business, the question is, how far into the future can you be more accurate than the historical average? And can you pick up on, is it going to be a wetter year or a drier year? And so evaluating this hydro forecast approach against the state of California's official models, it's called the Bulletin 120. This is saying if you looked when they issue their forecasts at the beginning of February for what flows will look like in April across California's 5 biggest reservoirs, can you pick up on that deviation from the historical average? And can you dial in the magnitude of what's going to happen? And again, the good news is that this approach shows a lot of promise. So pretty much across the board, we're able to pick up more accurately on, is it going to be a wet year or a dry year compared to the average? And how wet or how dry is it likely to be? And so as we think about what this means, let's take a quick step back to the sort of 3 sentences that I said at the beginning. In a world where more and more of the grid is being supplied by intermittent resources, having things that are firm or dispatchable like hydro can be increasingly valuable. But at the same time, we know that water is becoming more volatile. There are conversations about, is hydro even really a firm resource anymore? And the way that operators and trading teams can handle a lot of that is by saying, okay, let's understand what is likely to happen over the coming days and weeks and months, and make decisions based on that. And so these new forecasting methods are showing a lot of promise for being able to make hydro a really key part of that solution set going forward. And that happens both at the asset level, so operating individual assets more safely, you know, by avoiding floods and navigating drought, and also more profitably. But it's also really important for the grid overall. So as we move away from thinking of hydro as sort of this stable, fixed thing that just is what it is and the water is there when it's there, if you're able to look further into the future and say, okay, tomorrow, can we bid more confidently for how much water is going to be flowing past this point? Or over the coming months, can we manage our reservoirs in a way that really ensure that we'll have some stability? That can be really valuable. So my overall hope is that, you know, in this world where we're hearing more and more about the importance of solar and wind and storage, that operators that have hydro in their fleets are able to make the best out of it and able to help bring sort of this old workhorse alongside us into the 21st century. Thanks.
Okay, thank you for the interesting hydro talk. And we will be finishing up today with Dave Turner, who's a senior scientist at NOAA's Global Systems Laboratory, talking about the high resolution rapid refresh model. We heard Dev show that it did work best, but not at all time scales, you know, was everything perfect. And then we'll also hear about what's coming up for the NOAA high resolution modeling.
Thank you, Sue. Thank you. Yeah, so a little bit of work here done by the renewable atmospheric science renewable energy team that we have here in NOAA. Just to give you a sense, this is actually a fairly large team. And, so in Boulder, we actually have 4 NOAA research laboratories all co-located in the same building. And so, we have, various folks from all 4 labs that are been participating and helping to advance basically the state of the science in our weather prediction system, the high resolution rapid refresh, or HRRR. But today I'm going to actually show some results from some student interns that we had both last summer and this summer, just to kind of highlight some of their contributions also. To remind you, you probably are very familiar with this. This is the rapid refresh forecast system that we've been operating within the Weather Service. This was developed, at the research laboratories here in Boulder, and then transitioned to the operations of the Weather Service. But these rapid refresh systems initialize every hour using all the observations we can sort of get our hands on: aircraft data, surface net data, satellite data, et cetera, to initialize the model, try to get the best initial conditions, and then we perform forecasts. And you can see there's sort of 2 domains. The outer domain around most of North America is at 13 kilometers. And then we have 2 inner domains that are running at 3 kilometers. Those inner domains are the HRRR. And at the moment, the maximum length forecast is 48 hours, and that happens 4 times a day. This current version became operational in December of 2020. So some of the things that were changed into this current version, just to kind of remind you, is we extended the maximum forecast lengths from 36 hours to 48, in part due to requests from this community. We were able to argue for that. Changing various aspects of the physics to try to improve the representation of turbulent mixing, try to represent the influence of drag, which will slow the winds down to other aspects, and improve treatment of clouds. Clouds are going to continue. I will retire. We will still be working on clouds, but this is of course key for solar energy applications. One of the big things that we've really done is we've included smoke emission and transport from wildfires. And so I've shown an inset image here from just a couple of days ago, showing what the smoke forecast looked like over the Northeast, where there's been a lot of fire smoke blowing out of Canada. By improving the subgrid scale clouds and a bit from the wildfires, we've really reduced our bias in the downwelling radiation, shortwave radiation at the surface. But a lot of other aspects of things got moved and incorporated in this model. And really what's important is we're really in NOAA taking this approach to try to have this be really an Earth-centric model. We're trying to represent all these processes as well as we can: wind and solar, all seasons, all locations, both regional over the United States as well as global, to try to make it the best forecast system we can get. So a couple different applications I thought I would focus on. You've heard me talk before, and Stan Benjamin in previous years, we've been conducting these wind forecast improvement projects. So these are in collaboration with the Department of Energy's Wind Energy Technologies Office. And they're really this joint field campaign with and coordinated analysis afterwards. So the first one was almost a decade ago, really focusing on how can we better initialize the weather forecast modeling systems. The second one was really focused in complex terrain, and that was conducted in the Columbia Gorge between Washington and Oregon. The third one, which we are in the process of setting up, is really targeting offshore wind. And so when really looking at the offshore wind resources, you can see on the figure on the left, there's a lot of lease areas that are being discussed. Some of them are already been signed, others are in process, where they're hoping to put a lot of offshore generation. And the current administration would like to get to 30 gigawatts of offshore power by 2030. So what we're going to do is we're focusing in the New York Bight area, the figure on the right, to, there's already some turbines going in the water there, but to really get out there with some observations of wind and temperature and humidity, wave state, turbulence, et cetera, to try to characterize the atmospheric state in that environment, the sea state in that environment, and how well can we actually forecast, hub height winds in this domain over a range of conditions. And so this is going to be an 18-month field campaign really to get us there. To do a little preliminary work on this, we've actually started looking. The state of New York has these NYSERDA buoys that have been operating for a little over a year in the Hudson Bay area. And so we did an initial evaluation of the current version of HRRR v4, comparing to these Doppler LiDARs that are mounted on buoys. And so here's just an example of scatter plots. The top plot is for forecast hour 1. The bottom plot is for forecast hour 48 for this year of data. And so you can see there's some scatter. You can see the correlation coefficients are fairly high. R is 0.9 at forecast hour 1, decreases a little bit to 0.8. If you look kind of carefully, you can see at low wind speed conditions, right now the model is slightly over predicting winds, and at high speed conditions, it's a little bit under predicting in this type of scatter plot. We can look at it in a different way. And so what we've done is those buoys make measurements of the air temperature as well as the sea temperature. So you can actually take these statistics and break them up as a function of stability, where things to the right of the vertical dashed line are more stable, to the left are more unstable. And so you can look at the bias on the bottom, the RMS error on the top. The colors represent different forecast lengths. And so what you can see is the bias doesn't really change as a function of forecast length, but the RMS error does increase as you get out the longer forecast lengths. And interestingly enough, and somewhat surprising, is the differences as a function of stability weren't very large either. So this is already a very nice result if you're thinking about maybe using some of these observations, some of these forecasts. Second application, just to focus on a little bit, is wind ramps. Changing the wind produced power quickly over time is really important for us to try to characterize. Ultimately, that's the information you guys need to use. And so we'd actually gotten some feedback from Gunnar Schaefer back at SPP several years ago when V4 first became operational, saying that it looks like their wind ramp ability is very good in this model. So we wanted to sort of quantify that. So this is another student project. We're going to use 10-meter winds as a proxy for Haupt height winds, because as we just saw, there's not a lot of tall turbine data publicly available. And looking at a year of data. So here's just an example at one particular station over several days of the winds in black that were observed, and then the different model initializations at 0 and 12, just using this so the plot doesn't get too complicated, but you can sort of see in general, the model is capturing this variability in the winds well. If we run it through a wind to power curve generation, then you can see in blue are periods of time when you have up ramps, and then those red indicate periods of down ramps. And you can see that there's perhaps a little bit, less or a little bit more error in these situations. So our colleagues at the Physical Sciences Lab has built what they have is this wind ramp tool that is able to quantify, how well you do when you look at ramps as a change of power over a change of time. And so on the left is a change in generated power of 30% over a 2-hour period. On the right is a change of power of 60% or more over a 2-hour period. And the number of dots just kind of indicate how many ramps you had in those areas over that year. And so you can see the larger the dot, the more events that you had, for that change of power over change of time in that area. And so you can see these 30% changes over 2 hours occur fairly frequently, perhaps more frequently in the southern plains and closer to the front range, than you see for the larger area, for the larger changes of power over time. But we can look at a little bit in regions to get a sense of lower frequencies here, higher frequencies out here. We can look at how well did the model capture these events. And so using this ramp tool, you apply the ramp tool to basically compare the observations relative to what the model predicted. And so on the left again, this is the model skill at forecast hour 6 versus forecast hour 12. And so again, the larger the dot is the better the ability of the model to capture the ramps. And so you can see in the southern plains, there's some moderate to high skill, where if you move up into the Minnesota, Iowa area, the skill is a little bit less. But if we look at longer forecast lead times, 36 hours on the left, 47 on the right, those skills have gone down. And so this is something that we're continuing to work on. Changing topics slightly. So that was where we currently are. That's the model that's in operations at the moment. We are moving to a new modeling system. And so and this is, NOAA's been moving this way for many years now. It's going to their unified forecast system. And ultimately what we're doing is, if you were to look at all of our short range, high resolution models in operations right now, there's half a dozen of them. And they have different model physics, different domains, different lead times, maybe even different initialization approaches. And ultimately that's too many modeling systems to maintain. So the unified forecast system approach is, we're going to take all those modeling systems and basically retire them in favor of a single modeling system that handles all the requirements that those modeling systems are trying basically cover. And so this new modeling system we're developing is called the Rapid Refresh Forecast System. If you're a government employee, you need to be able to pronounce acronyms. So we call this RUFUS. And so the idea with RUFUS is that it's going to replace not only the HRRR, but all the other sort of storm scale models that you may be using in your decision making right now, like the NAM, the high-res NEST, et cetera. And that is being targeted for November of 24. So a few details about this. First of all, you can see the two HRRR domains on the left there, the two green ones. The RUFUS domain is the one in yellow that covers that entire, basically North America continent. It extends much further into the Atlantic, so we'll be able to do a better job capturing and representing hurricanes that may be impinging on the East Coast. It gets much further into the Pacific, so it can actually cover Hawaii also, but it'll do a lot better job capturing atmospheric river events and other things that moved on to our West Coast, as well as what's coming from the north. The middle plot shows the vertical resolution. In round numbers, our vertical resolution is going to be about twice as high, than we have with the HRRR. But the physics that we're going to use in RUFUS is effectively the same physics that we're using in the HRRR, albeit improve it. We've had several years, we're continuing to do science and an improved representation of all these physical processes that the model must represent. Just to give you a sense of where we are today, so this plot was just made last week, and so it's showing basically as a function of time of day, the bias on the bottom and the RMS at the top of 10-meter winds over the continental US between the HRRR in red and the RUFUS, the developmental RUFUS in blue. Now we're still doing development, but you can sort of see that in a general sense, the bias characteristics are pretty similar. The RMS characteristics are, maybe a little bit inflated. As we all know, you can hide lots of sins in a plot like this. And so, we're continuing to try to improve this in different weather conditions and different events. But, as I look at the RUFUS, is again going to assimilate everything that we've been assimilating before. We're going to do a lot better because the domain is bigger to try to bring in more satellite data. We've been improving our data assimilation methods to initialize the model. But important for this group is that it's an ensemble system. And so when RUFUS becomes operational, it's going to be producing 10-member ensembles, every 6 hours. And so you'll be able to have some probabilistic information that you can look at. Now, most of the ensembles have been tuned to be looking at convection, and so we still need to do some evaluation of how well that these ensembles capture the spread and the skill associated with wind and solar energy, and that's work that's ongoing. But to give you a sense of some things that can go, here's an example of an ensemble system, and I'm looking at cloud cover, low cloud cover, that's greater than 50% over the West Coast. And so this is sort of the mean condition right here, the probability of a low cloud cover greater than 50%. And so the colors on the bar are ranging from, in the yellows, 80 to 90%, down to 30% in the blue. But you can also look at the sense of that's so the probability of cloud cover above 50%, but we can look at what's the timing of this. So when do you think the onset of these clouds might happen, where the cloud cover is greater than 50%. And so the purples are showing that the onset of the clouds are happening in the first few hours of the forecast, where when you get up to the reds, that's like about 35 hours of the forecast. We can look at, a couple of last week, we had very low winds in the plains. And so this is showing basically what's the probability of cut-in happening. What's the timing, the mean timing that winds would actually exceed the cut-in speed, because we had very low wind conditions over the plains. And so in the mean sense, it's looking like it's going to be about 43 to 45 hours across the central plains. But again, you can ask the question with ensembles, what is the earliest timing when you might get the winds above that cut-in frequency? And so now you're seeing, depending on where you are, times from 27 to 35 hours. So I think these ensembles allow us to sort of pull this information apart in different ways to look at timing of events as well as probabilities. So just to kind of wrap up then, version 4 is what's operational, and it's doing those longer forecasts, again, motivated by input from this group. And lots of new products, in particular the smoke, continuing trying to improve our precipitation typing, et cetera. But we're working on the RUFUS now, and the time schedule is that we would become operational in November of 24. And so there's a lot of changes that are making there that we have to, sort of improve and understand and characterize. But important for this community is A, all those other storm scale models are being retired. And B, this is an ensemble system to replace that. So, there's a lot to get used to. And we're continuing our research. So thank you.